Welcome. I will be presenting on Trustworthy Actionable Perturbations, our publication in ICML 2024. To motivate our work here, we want to consider that machine learning classifiers are increasingly being used in these very high-stake applications like finance and job recruiting, where they have a profound effect on individuals' lives. And the question we want to ask is, who do these classifiers really help? And the answer is the institutions, the bank, the college, the company. They're not really helping these individuals who they're affecting so profoundly. So our question was, can we use these classifiers to help the person turn down for a loan or for a job interview or who doesn't get into the college they wanted? So our outline for how we do this, for our method, we take an input X, and this has got an undesirable classification. Maybe they failed their loan application. And all of these desirables, these are important parameters. What kind of changes are actually possible in the real world? What's the cost? What are we trying to minimize here? And what's the goal of our change? And we can use all that to create a trustworthy actionable perturbation, or TAP, which is a modified input that gets these better classifications. We also implement a verification procedure. This verification procedure tests whether our modifications are acting adversarially, or like an adversarial example, meaning they fool the classifier, but they don't change the true class probabilities, or whether we're actually having the intended effect in the real world. Our outline for this presentation is we'll first talk about some related concepts, and then we'll go in depth on these desirables, which will lead us directly into a definition of TAP and a way of generating TAP. We'll next talk about our verification procedure, and finally we'll discuss our experiments and the conclusions that we reached. Now, the most closely related concepts are actionable counterfactual explanations and algorithmic recourse. Just like TAP, these give advice based off of what a classifier says, and their advice is meant to be possible, feasible in the real world. However, there is a difference in our intended goals. These previous methods just want to change the classifier's final decision, loan rejected to loan accepted. We have a much more flexible definition of goal. Also, in terms of what we're trying to minimize, previous methods have tried to make the smallest change, generally according to an L norm. We feel it's very important to measure the actual real-world expense of making a change, which is often not really found in this L norm. Finally, these previous methods are created in a way very similar to adversarial attacks, which cause misclassification, but they don't change true class probabilities. We create our TAP in a similar way, but we've added this verification procedure to defend against this adversarial behavior. So let's talk about these desirables. What do we want to happen? The first thing is we want our changes to be possible. We want things that can actually happen. We don't want to tell people to do things like decrease their age. And we define this through the actionable set A of X, which is all of the things we could change X into. And here are some examples of what that might look like for the loan application scenario. Next, we want efficiency. We define this function D sub X, which represents the real-world cost of making a change. We have a few examples here. Let's talk about the one in this middle column, where we're trying to create a better course of medical treatment, and perhaps the thing that we'd want to minimize is the difference in hospital staff hours and the difference in medication costs that come with a new treatment. We wouldn't want to increase those values too much. Now let's talk about our goal. Our definition of goal is very flexible. It uses this target set T, which is just the set of all acceptable outcomes. Now we have a few examples here. Let's discuss the one in this last column where we're doing salary prediction, and we want to have somebody who wants to have a high salary in the future. So we might require that there's a 50% chance they're in these very high salary classes. But if the individual also wants to avoid very high risk strategies, they don't want something that could result in high strategy or unemployment, we'll also require very low probability that they're in this undesirable class. And this is the way we've gone about formulating our target sets, our goals. But once we have this target set, how do we measure our progress towards our goal? And we think this needs to be done in a principled manner, so we use F-divergence, which is a family of measures of statistical divergence. This includes KL divergence and total variation distance, all of the common ones. And we just define dy as the distance from our point to the closest point in the target set. Now, this is a minimization problem, but we analyzed it and we show that this minimization problem has this nice closed form solution. It has this piecewise form, and this is in fact even continuously differentiable, which is very useful. So now that we've defined what we want to happen, we can define a TAP. An epsilon delta trustworthy actionable perturbation, or TAP, is simply a point that has cost less than epsilon, gets us within delta of our goal, and is actionable. To create one of these, we just create a minimization problem, which is the weighted sum of our distance to goal and the cost of an action. Now, our lambda here is a parameter that we can use to tune the effort-reward trade-off, or the trade-off between epsilon and delta. The other thing we want to note is we don't have access to the true class probabilities y of x tilde, so we use our classifier's estimates, m of x tilde. However, an issue arrives when we replace y of x tilde with m of x tilde. That issue is our optimization problem actually fits the same form as the general optimization problem used to create adversarial examples. And we know adversarial examples don't change the truth, the true class probabilities, the results in the real world. They only change what the classifier says. They fool the classifier. This is also the case with previous works such as algorithmic recourse. And we really want to have an effect on the real world, which is why we introduce our verification procedure, which we'll explain here. Now, detecting adversarial examples and adversarial behavior is actually very well studied and a very difficult problem, but we have an advantage. We know the original data point x and exactly how it was changed, x tilde, so we can use both of those to detect whether x tilde is affecting the true class, and we should pass that advice to the user, or whether it's acting adversarially, and that is not useful advice. The way we take advantage of this is we create this verifier function that takes in two inputs and outputs the probability they're in the same class. This is pretty easy to create. We just take our training data and we use it to create pairs. Pairs in the same class we label with a 1. Pairs in different classes we label with a 0. And we train a classifier to predict those labels. This is kind of a new and a different type of learning scenario. So we analyzed it and we did show it's PAC-learnable, and we even have our PAC bounds here at the bottom of the slide. So now that we've got the verifier, how do we use it? The verifier predicts how likely things are to be in the same class, but we don't want to rule out things just because they're likely to be in the same class, because that would rule out low cost, low reward advice. Instead, what we do is we notice that this probability that two things are in the same class can be estimated two ways. One with V, and also by taking the inner product between our estimation of the classes of X and our estimation of the classes of X tilde. Now, if X tilde is adversarial against M, we would expect our estimate using M to be very small. M would not think that these things are in the same class, but V, which was never showed to our optimizer, and we have no reason to believe that X tilde would be adversarial against V, that would actually predict a very large probability that they're in the same class. So by looking at the difference between these two estimates, we have an indication of how trustworthy our example is. And as long as that difference is below a certain cutoff, we trust that TAP as likely to have the intended effect in the real world. So now that we've defined how we create TAP and our verification procedure, we're ready to talk about our experiments. We tested our method on a variety of real-world data sets from different fields and compared to some of the most common similar counterfactual methods. Here we've got results for a single individual in the adult income data set. Our results are in blue here. On the x-axis is the cost of a change, and on the y-axis is how close that change gets us to our target, the delta. And as we can see, our method produces a much greater diversity of low cost, low reward results, and also high cost, high reward results. We also notice that our method is just generally a little bit more efficient. It gets better results at the same cost, but this is just one individual. So let's look at an entire data set. Here's the German credit data set. And each one of these bar charts represents how many individuals we were able to move within a specific distance delta of our target set at different costs. And you can see our results in blue are always higher. We're always more efficient. We're able to get more results for the same cost. On top of that, we're also displaying the results of our verification procedure. Here we have what happens after we verify. Notice that the red bars here come from the Carlini-Wagner attack, a very well-known and a very strong adversarial attack, and we are 100% effective. After verification, we always know that those adversarial attacks are not going to have the desired effect. But additionally, we also notice that our verifier is ruling out a lot of the tap and counterfactuals, that a lot of the advice these other previous methods and our method provide are actually not going to have the intended effect in the real world. This shows that the verifier is very important. So what conclusions can we reach? Well, here we've made the contribution of this framework for using classifiers to help change undesirable classification and really make them useful for everyone, not just the institutions. We also developed this novel verification procedure, and we show that our method does indeed come up with more efficient advice. In the future, we'd like to incorporate more sophisticated actionable sets, include some interdependency between variables. We also would like to look into improved methods to solve this optimization problem that can be difficult. And we believe it would be very useful to incorporate some of the ideas behind causal machine learning to also ensure that we're going to have the intended effect in the real world. Thank you very much for your time today.